Yes, Noah, proceed. Noah, this was for latent TB. Noah, is this for latent TB?
Yes, it's the one.
Okay. You have it back. You've gone off. Okay.
I think you can see it now.
Can you put in presentation mode?
Yes.
Sorry about that. You can just leave it there if it is. Yeah, Professor, members of the group, let's take notes such that we refine our work after.
Okay. Because the first assumption is that all newborns they don't have tuberculosis. The second assumption is that the birth equals to death. Or I say natural birth equals to natural death. And that leads to another assumption that the population is constant at all times. Now, you have not indicated who is transmitting. I don't know how this S gets infected or gets exposed. Who exposes S? That one is not indicated. And then D, is D for dead? Hello? I want to know what variable D is.
Noah, can you speak?
Oh, D was for, yeah, it's the compartment for those who died. Okay.
Who died from tuberculosis?
Yes.
And that means that the exposed people don't die from tuberculosis. Only the infectious ones die from tuberculosis, or that you can only die from tuberculosis after the latency period. Then the other thing is that you have constant death from each of the population. You're saying that the number of people who die in S due to natural causes are equal to the number of people who die in E, number of people who die in I, and number of people who die in R due to natural causes. Is that what you wanted to mean?
I think, yes, that's what we wanted to mean. Yes. That's why the variable is constant.
So that means that what the model means is that assuming you have 100 people with tuberculosis, 100 people in your population, maybe you divide by your 5 compartments, let's put 20 in each. So you're saying from each of the compartments, the same number of people are dying. You have 10 dying in S, 10 dying in E, 10 in I, and 10 in R.
And I think logically that may not be the case because, for example, if somebody is just exposed, cannot be the same number dying like I.
Yes, that is true.
But they're dying of natural death, though. It's so their death is It's not directly.
But again, from the biology of the disease, we know that if somebody is infected with TB, they are prone to other opportunistic diseases like HIV, like others, like
it compromises the immunity.
Exactly. So we cannot still compare Abel, who is infected with TB, with Adrian, who is susceptible to getting TB, and saying they are likely to die at the same, even if it's from natural death or from other death conditions. They may not be the same, really. I don't know.
Oh, yeah, that's true.
They cannot be the same. And I saw a question in the chat, someone asking whether mu is a rate or a number. From what is represented here, it is a number, not a rate. But mu should be a rate. Then if you can explain why no dots and why dots imply.
Yeah, the data used was from a dots study in Uvaga.
Then?
Actually, what you would say, Noah, is that the Y was an intervention. That Y is representing an intervention. The TB, the directly observed therapy, is an intervention
yes,
to the people who are infected with TB for them to recover. So it's like it's a treatment intervention, Prof.
Yes, but the way it is presented, it means that the people who had intervention and the people who didn't recovered at the same time.
Yeah.
But is that the case, though?
No, it isn't.
So you also have to fix that, because it is not. You have some people dying, some people recovering, but the people without, because you have no dots, the people without that intervention, they don't recover the same rate as the ones on intervention.
Yeah.
So you must have, definitely people are recovering. Let me just say, I have a class, but let me just note this down. I think I'm going to push the other one. If I can have an hour in between for me to come and do the sensitivity analysis, I'm going to steal some time to do this model for you the way it should be. And I guess other people can also, let me just...
in your schedule, is it okay to do the sensitivity analysis even now? Say that you go for once, or you have another session now, another class now?
I have another class at 10.
Okay.
Want to ask them that we can push a bit, and then I leave them with an assignment. If I can leave them with the assignment, then I can come back. I'll definitely communicate to, I don't know who called me yesterday, I think Nakasuchi.
This process, yes.
I can.
Yeah, Professor, thank you so much.
Yeah, so let me just try to do this model here, the way it should be, based on the assumptions that you have made. And you should also, and for the rest of you, you just go back to the assumptions. So no external infections. I think you just have to say no exogenous infection. Exogenous, yes.
Okay.
Okay. Then you also have to tell us who is infecting S. Is it the E or E and E plus E or I? Who is infecting S?
Yes.
Now I'm asking because when I do this model, I need to know such that I can show you how you should do this compartmentalized diagram, because these models is simplified. They easily convey the message you're going to put in the equations and the mathematics. So it has to be very clear for anyone to understand without mathematics. Before you come to the modeling, the data, the what, somebody knows what you're doing. So is the exposed and the I transmitting to S, or only the infectious, the I? What is your assumption there?
Let me ask a question on the model itself. Does that mean I should have an arrow coming from I back to S?
No. By just showing, you see this beta, movement from S to E is an interaction between two people.
Yes.
Movement from E to I is a transition from one state to another. So the interaction has to be shown who is interacting with who.
Oh, okay.
So that's why I'm asking who is interacting with S to have E.
It's the population at the start that was already infected with TB.
But which one, the E or the I?
I think it's the E.
I does not infect people.
Yes, that's because
No.
everyone in the population was, let me see, according to assumptions, I think.
No, the assumptions are not there. So you see why you have to have clear assumptions. Because when I say what you're making assumptions that are not even listed here. By looking at the model, there are some underlying assumptions. So maybe what we do.
Yes, Prof.
Usually the people that have symptoms, people who are coughing, are the ones who transmit, right? I don't know the period for tuberculosis. I don't know how long it is. So I'm going to assume you will correct it later on, but I'll show you how you should do these models, and to the rest of the team can also do that. But I'm going to just make an assumption. I'll find out if I get a minute or two, the latency period for tuberculosis. TB, then if it is quite long and people exposed can transmit, then I'll just revise and include interaction between S and I. S with E and I.
Okay, Prof.
In the meantime, I think the rest of us can also revise our models based on the few ideas we have had. Then you will have to see how you model, how you do this compartmentalized diagram, because they are also mathematics themselves. So let me see if I can set the other class off such that they continue with the assignments. Then I can come back here as you do that. Or if you're done with that, you can pick one of the models amongst yourselves. You choose which of the simple models I shared with you for each one to use their own assumptions. Then you can see how different the models can become by just one simple assumption, how results can change. Okay.
Yeah, thank you so much, Professor. We shall be waiting to hear from you.
Okay, I think you're going to remain online. Let me just leave for now, and then I'll log back in.
Professor, can you stop the recording?